Okay, so our last lecture this afternoon is by Professor Kenji Fukaya from Stony Brook. He's going to speak about Functorial construction of Lagrangian Floer theory and its possible applications. Please.
Thank you very much. So I'm very happy to talk with this conference. And the title was a bit abstract because I didn't decide what I'm going to talk, but now I have more concrete title. I want to explain how to use Lagrangian correspondence to prove the homological mirror symmetry in a certain case. And so the idea I am going to talk is supposed to work in more general case, the so-called SYT vibrations. But I want to restrict myself to the case of 2L tori because the best construction is written only in that case. And also, so I want to start with mentioning that there's a work by Subotic more than 10 years ago, and he constructed something called infinity bifunctor on the category of Lagrangian Floer theory, by a category over T to N to itself. And this functor is, I think, Q in that case is a mirror to the tensor product. So this category is known, is expected to be isomorphic to the derived category of coherency of the mirrors. And the coherency, you can define derived tensor product. And so you look this derived tensor product in the symplectic side, you get this bifunctors. And okay, yeah. So now I want to define how to define these functors, and I will use SYT vibrations, and I want to find some Lagrangian correspondence. And so what is this Lagrangian correspondence? So in this case of T to N, it is a fiber of Tn, and the fiber is Lagrangian from both. So we consider this L in a triple product of T to N. It's a triple XYZ, so that the base point of this 3, 6 are the same point in Tn, and Z is X plus Y. So what is means is X plus Y. So we have this SYT vibration, this is Lagrangian Floer vibrations, and the fiber on T on Tn is Lagrangian Floer, and we fix some sections on this SYT vibrations, and then so we fix these sections, and then then a section structure of abelian group or the Lagrangian fiber is defined using this section, so that the point of the section is a 0, the unit. And you have Lagrangian vibrations, and this Lagrangian Floer has a coordinate which is called the action coordinate, which is something like a flat structure. And you fix this base point, it has a structure of abelian group in the way. So each fiber has a structure of abelian group. So you consider this triple, so that this 3 point is in a same fiber, and the Z is X plus Y. So this Lagrangian correspondence in the sense of fiber-wise sum of this Lagrangian T to N. So this is the Lagrangian sum and fold of triple product, and this is the so-called Lagrangian correspondence between two products of T to N to T to N. And so this is the construction of Lagrangian correspondence. You can see that this kind of correspondence is supposed to exist in more general XYZ cases. But in the case of there's a singular fibers, there is some difficulty. I need to think more about it. And in the case of T to N, there is nothing. So now there is a general theorem which is started by Wilhelm Woodworth and Moore and Lagrangian Piasky, and I wrote some papers 6 years ago. If there is a Lagrangian correspondence for one Lagrangian sum of one symplectic manifold X to other symplectic manifold Y, then there's an infinity functor from category X to category Y. So this is general constructions. The Lagrangian correspondence gives an infinity functor. Definitely. And I want to, so I apply this theorems to this particular Lagrangian correspondence. So it gives a function W from this two product of T2N F, T2N F to T2N F. So that is this function. And this Bonic constructed this function many years ago. And he checked that if you use your mirror symmetry, homological mirror symmetry, this function coincides with the tensor product function in the mirror side. And I do not So I do not want to explain the proof of these theorems because it is a false story. The paper I wrote 6 years ago is now 300 pages, so I cannot explain this all. But anyway, so I want to use these theorems, and I want to explain how we can use this particular function W to study homological mirror symmetry on T2N. And as I said that this story is expected to be generalized to more general SYG vibrations, but but it is not yet done. And I need to mention something. Yeah. So in this kind of Lagrangian correspondence is now there's a project to cook up this correspondence in general cases by Mohammed Abuzai, Nathan Bodman, and my student Yunpei Liu, including some singular items. Okay. But today I don't want to talk about that project. I want to restrict to the applications of these functions to study mirror symmetry. And in this mirror symmetry SYG tabulation, so I first fix one section, S0. It gives a unit of each fiber. And I want to assume another section, S1. And this S1 with another section, which is something like a positive section. And I mean positive in one way. So we consider this universal cover of T2M. This is R2N, I'm sorry, this is R2N. And the bases are universal cover Rn. And the universal cover of T2N is regarded as the cotangent value of Rn. So you got the universal cover in your SYG variations in T2N case, it's just T star Rn to Rn. And then this S0 is a zero section of these vibrations. And S1 became something like a graph of the exterior derivative of some function Q. And Q is a positive definite scalar form on Rn. And its positive definite is related to this positivity. And so there we have this two Lagrangian summand code. One is the image of S0, that I like L0, and the image of S1 that I wrote SL1. And they under mirror symmetry, L0 is expected to be a structure sheaf of the mirror tori, and L1 is expected to be an ample line value of the mirror mantle. So in the case the mirror is an Abelian variety, then you can expect to have two particular sections, mirror to structure sheaf and ample line value. And of course, in a more general SYG vibrations, with the mirror with the projectile variety, you can still expect to have two sections like this. So this is the situation I want to start. So the simplest example is the following. You can just take T2N, it's just R2N minus the standard T2N. And omega is a symplectic form. And then this SYG vibration is XY go to X. X is the and then S0X is just X0, it's just this kind of sections. And S1 is this diagonal section, XX. Here two sections. Now, in this case, Lagrangian correspondence is XY1, XY2, XY3, and Y3 is equal to Y1. It's very simple. Lagrangian summand code, the triple product of T2N. So now, we have this function W. So for the object, this W is called that. You have two Lagrangian summand code in T2N. Then this W of L1 and 0 with L2 is another Lagrangian L. And L is XY1 plus Y2. XY1 is in this first Lagrangian L1. And XY2 is the second Lagrangian L2. You can say fiber-wise product of this Lagrangian manifold, and that is this because that's what this function do for the object. But the important point is that this gives some functorial constructions for the play of more and the products. So now, let me record that L1 in this case is just a subline diagonals. And I want to consider this W of L1 L1. So this is x2x. So it's a kind of graph of 2x. So it's something like this, right? So the first one is something like this. This is x1. This is L1. Then next one is something like this. This is L2. And L2, sorry, L2. You can see that the slope is getting bigger. So I want to define inductively LK so that LK plus 1 is W of LK and L1. You know, it's a phasor function. So L1 became O1, ample line sample, and LK became the OK, phase tensor product of ample line. So now what we do is just we take this player quantity of L0 and LK and take the direct sum of all three. So that is this A. And you know, so if you believe this is commercial symmetry, it is just take a section of all OK. And that is, I think, if you know the geometry, it is a homogeneous coordinate ring of the projection of the line. So, and we have a positivity, which means that all intersection is actually positive. So the player homology, and the player homology has a generator. I forgot. So P is contained. Right? Is contained. Oh, yeah, that's my handwriting is terrible. Right? So Fourier chain complex is generated by intersection point, but in this case, this boundary point is trivial, so it's just generated by the intersection points and over subsequent nodes of field. I don't want to explain so much. So this is just a player homology, and its rank is I think k to the power n, I think, not square. So it is just some kind of rational form. So this is A, and so this is just the arbitrary group. But the important point is that we use this functor W, tensor product functor, to define the structure of gradient commutative ring. So the claim is that this A, the direct sum of player homology, is a gradient commutative ring. So how to do it? So let me call the W is a function of f of Tn times f of Tn to f of Tn. This is an infinity by function. What it means? Suppose that L1, L2, L1 prime, L2 prime is the Lagrangian sum manifold of Tn. Then you have this player homology of L1, L2, player homology of L1 prime and L2 prime. And this product goes to player homology of W, L1, L1 prime, and W, L2, L2 prime. So this is what this infinity by function means. So in our case, if you consider this LK1 and LK2, this W makes it LK1 plus LK2. This is just by definition. And then this function, this group morphism became a player homology of L0 and LK1, tensor player homology L0 and LK2, which goes to player homology of L0 and LK1 plus LK2. So this is a kind of map, and this is a product of this ring A. So K gives a gradient, and the gradient K1 and gradient K2 element, and the product which is gradient K1 plus K2. So this is the gradient ring. You get a structure gradient ring, and this product is associative, and this associativity came from this something like a composition of Lagrangian correspondence correspond to the composition of the entity factor. And you can use it to prove that it's associative. And this product is commutative because the group structure each fiber is abelian. So we have this the XYZ is contained in this Lagrangian correspondence, even only YXG is contained in this Lagrangian correspondence. So this implies that this product structure is commutative. So we obtain this graded commutative ring A. And so you know that for scalar symmetry, so you assume that you know the proof of you have already for scalar symmetry, and LK goes to OK. Then this A is the direct sum of the cohomology. It's only zeros cohomology. Cohomology of OK, and that is a homogeneous coordinate ring of your abelian variety. And so, but actually, I want to use this A to prove homoscamilla symmetry. So we are not supposed to use this isomorphism. So we don't use homoscamilla symmetry. We have to use this to prove homoscamilla symmetry.
So why are we doing the
Yeah, because we have this 0 and this 1, and this 1 became non-random. So it is hard. So we have this A, graded commutative ring, but we still do not know that there is this kind of thing that I want to prove. So the first theorem is that this graded commutative ring A, I just defined, is finitely generated as lambda algorithm. And probably this is the kind of most non-trivial part of the whole story. In this case of P2N, actually, I think it's not that elementary, but this finite generatedness is somewhat non-trivial. You define it as a kind of direct sum of their model. And so once we know that, I'll explain how to prove it later. So once we know that this A is finitely generated, then in a general algebra of geometry says that you have a very commutative ring which is finitely generated over ground field. You get some projective algebra variety, project A, whose point is homogeneous ideal. So you took up, so using only symplectic side of the story, you took up some projective algebra variety. That's the first step. Okay, so now I want to, so next thing is I want to identify what is projective algebra variety, and I want to show that it's actually algebra variety. So how to do it? So first record that SYT mirror to the, so there's a notion of SYT mirror to the state M. And it's
so it is generic. So there could be a lot of for the drop break, but in this case we don't seem to practice in our argument.
I am just constructing some mirror manifold. And so you're starting another argument. The way that we have to have some quasi-coherency on this vertical right. And that is reality. So I don't know how to use the quasi as a gray. I use only Lagrangian.
But that might not be that.
And yes, split generation. Yeah. So we consider this. So to identify this projective variety, we need all the following things. So XYZ mirror of this third-dimensional tora is a pair of the point XY star. Xi, so this is M. X is an element of the base space, and so this two is the discrete. X is element of Tn, and Y star is a flat bundle over this Lagrangian of fibers, and it is a flat bundle with Novikov ring as a coefficient. So its element is Y1 star, Ym star, and Yi is A0 plus T lambda I AI. T is the formal element in the Novikov ring, and A0 is non-zero. It's a complex number and it's non-zero, and lambda I is positive, which is a kind of unit in the Novikov ring. So it's a monodromy. So usually you take U1, it is Novikov business, we use this kind of things. So this is an element of the mirror, SYZ mirrors. And the next frame is that if you have an element of this SYZ mirror, this determines a homogeneous ideal of our very competitive game. So that's the second statement. So it implies that any point on this mirror gives a point of this projective algebraic variety. So you have this mark. And the next statement is that this mark is an isometric. So this projective algebraic variety, which I took using this counter set over a someone called after coincide with XYZ. And then for the homological mirror symmetry, we consider M another Lagrangian submanifold and B the logical chain. I don't want to explain it, but it's something flat bundle which makes it Floer theory to be very defined. So now I want to construct this MK so that M0 B0 is just this MP. Then I take this tensor product functor, this MK BK and this L1. It is MK plus 1 BK plus 1. Inductively you define MK BK. And now I put this Floer chain complex with M0 and this MK BK and take sum over all K. And this is a Floer chain complex for this LK. And then what I show that this B is actually a graded differential module over our graded compatibility K. That again came from the tensor product function because the tensor product of this guy with NK prime is just NK prime, NK plus K prime, BK plus K prime. So the tensor product function defines the module structure, graded module, relative graded module structure over our graded compatibility. So we have so this just comes from W. And one last thing is I don't know whether this module is finally generated or not. In the case of A, graded compatibility, as I explained, I conclude that it is finally generated. But this module, I don't know whether it is finally generated. And I have a suspicion it is finally generated. So it gives, you know, so this is a graded differential module over this A, graded compatibility. So this graded differential module gives a quasi-coherence sheaf over projective algebraic variety. It's not, if I can prove it is finally generated, it implies that it's an object of coherence, there are categories of coherence sheaf, but since I don't know whether it is finally generated, it gives only quasi-coherence sheaf. But this is but this construction is still okay. And there we have this quasi-coherent sheaves on this B. So now the last claim is that so this correspondence, I mean which associate M to this quasi-coherent sheaf gives induce an isomorphism between there are the category of split closure of the category came from Lagrangians to there are the category of coherence sheaf on a project. So I want to prove that this chain complex of quasi-coherent sheaf is actually weakly equivalent to the coherent sheaf, chain complex of coherent sheaf, and this map induces an infinity homomorphism, which became an isomorphism of the category. So this is some kind of homological mirror statement. So that's this stories. So do you have any questions you want to talk about? Yeah.
Is this way to make this thing of
Yes, it's finally detected. The point is that we learn to pick it up from only this time. And I have to say that this homological mirror symmetry of chloride is already known. There are several proofs, especially Mohamed Abdai's story of family homology gives homological mirror symmetry of Lagrangian variety already. And but the proof I want to explain is somewhat different. And I also expect that this argument can be generalized to more general XYZ foundations. And you will see the proofs that many parts I believe can go through to that reality. But I restrict to this case because this harmonic correspondence factor is written only in this very simple case of P2N. And the proof itself, as I explained, is not so difficult. So I think you can get some idea how to use these things. And if one compare these constructions to the construction by family pair models, the difference is the following. For the family pair models, people use this XYZ fiber, Tn, as a kind of test function, and the player model against this Tn gives this mirror construction. In this case, we don't use Tn. Because we use this family Fn. It's a kind of mirror to upper one. And so we are responding counter remaining again. This makes story a bit simpler. And also the difference is that if you call the Lagrangian fiber to Tn, the player model between them is actually trivial because they don't interfere. So the family of Lagrangian fibers itself still has some structures, but the structure does not come from there. It came from something else. And in our case, we have used this LON, this family of family. This family of some code, and they interpret, and the main structure, the ring structure, in the homogeneous coordinate in the mirror, just came from the player theory on this LN. So in that case, in that sense, this LN or something more than that of fiber. You just use this LN itself and the player module with them. Then you can just hook up this player manifold. So in that sense, it gives some. This is an advantage, but yeah. But one assumes that the mirror is not important for this. It's probably player module has a less assumption. But and also, I believe the proof of this is a bit somewhat simpler than this family player model.
People will know what the bot can get to the survey itself.
Yeah, I don't know. Okay, so now I want to explain the sum of the proofs. So I start from theorem 3. So theorem 3 was the point, right? We have a point on a S. Oh. So theorem 3 is a point, right? If we take a point on this SYZ mirror, it gives the homogeneous ideal of this project by writing. So how to do it? So I want to prove this. So we first consider the point with this Lx and y star. It's an object of our category. And so we consider this Lx and y star, and we consider player emoji of this with this L0 and Lk. And the observation is that this player emoji is actually rank 1. Why it is? So this is L0, it's something like that, horizontal, and Lk is something like this, and Lx is vertical, and L0 and Lk are actually sections, so it intersects Lx at just one point. So this means that this guy and this guy are rank 1, just one element. So now we consider this the product structure of player emoji. So we consider this player emoji L0 Lk. And player emoji of Lk, Lx, y star. And this product goes to player emoji L0, Lx, y star. So this is both this grounding. So this M2 gives the map from the player emoji L0, Lk to lambda. And this guy, this guy has many things. So you have a map from the emoji L0, Lk to lambda. This is divided H, X, Y star. And we define the direct sum of the kernel of this map as mx y star. So it is a gradient subspace of A. And the claim is that this mx y star is an homogeneous ideal. And those homogeneous ideals which correspond to this particular point. And you look at all the constructions in the mirror side, you will see that this should be the correct one. So how to prove the level?
You mean to actually add this picture down on the fine base, or it's just
No, this is T2M. Yeah, yeah. So the proof uses this commutative diagram. So this looks rather complicated, but this is something like a functoriality of our W. So first, let me consider this side. So this is the definition of H. So L0 Lk1 and Lk1 Lx, and this is so this H is a multiplication, so it goes L0 Lx, and then this is L0 Lk2 and Lk2 and x, and it goes to L0 Lx. So this both H is something like a product in this cavity. And then downstairs, so we take this guy, and W gives the map. So this guy, so you take this delta product of this. So you have this L0, and you take the product of this Lk1 plus Lk2. Yeah. The product of this guy goes to here, and this guy to Lk1 plus Lk2 to Lx, and then this guy to Lx and Lx. After you have a y star, and this is y star, and this y star square. But anyway, you know this and the W is so the fact that W is a identified function, in particular implies that this diagram commutes. So that is W commutes with this M2. That's a part of the solving which is functoriality of this contrast. So we have this commutative diagrams. So what it implies that in S1, so in this diagram, if S1 is here, and T1 is here, and T2 is here, and here it goes to T1, T2, right? And then, for example, this goes to 0, and this goes to something, then this should go to 0, right? Because of this commutativity. So it implies that if one of these factors lies in a kernel of H, then the product also lies in a kernel of H. So this just means that this M is a ideal. So this is very simple argument. So in this very simple argument using this functoriality, we show that this M is an ideal. So this is the way to obtain homogeneous ideal from the point of the S1 unit. Okay. So this is so now I want to explain this theorem 1. That is whether the commutative ring is finitely generated. So first observe that we have this SYZ population T2n to Tn, and in the general story, the base space of SYZ population has an integral affine structure, and that came from the kind of the cotangent boundary of Tn has a lattice structure, which came from this experimental fibers, and we can use it to obtain integral affine structure in base space. So this guy has an integral affine structure. So it means that we can make sense the notion of rational point on the base space, and locally it is something like Rn divided by Gn and Qn or something like that makes sense. So we consider the set of the points so that it's k to the power k times x is the integer point on this integral affine structure. So this is something I wrote this, and then the lemma is that we consider the expression of homogeneous K, and you take this all the rational point by this H, and it is injected. So what means that why this lemma? So the proof of lemma is actually easy. So for example, so we take this intersections of L0 and L2 is these 2 points. Then we can just take this 2 x and x prime, and then if you consider this guy, well, at x prime, this one is a leading order, and x, this one is a leading order. And you look a bit about this for this simple product is doing. We can just calculate this h in a leading order term. We can prove this lemma. And what's good about this lemma is that we can calculate. Yeah, we can detect the element of this square body just by taking a value as a rational point. So I mean, so the difficulty to prove this theorem one is that this product structures on a diagram of their motif is defined by using this entity bifunctor W, and the construction of entity bifunctor W is rather complicated. Actually, the proof I gave using this modular zero cube. And so in this case, it is using Floer theory over T6M. So to look directly is a bit cumbersome. But using this, we can just take the value of this raster point and to calculate this product. So that's the idea of this theorem. So now next we observe that this intersection of L0 and K is just this raster point, right? So this is L2, and this that intersection is 1, 0, and 1, 1. So the story is similar. So this intersection with L0 and K is actually a rational point on the space space. So we just so now this corresponds to some point P, which is L vector divided by K. L vector is something like a d to the power of n. So we have this rational point. So we write this corresponding element as S of L vector K. So now I want to calculate the product of L vector K and L prime vector divided by K prime. We have these two elements there only, and we have this multiplicative structure on the diagram of the player only. And the claim is that this product is just so you take a sum of numerator and sum of denominator, and the sum constant. So this is a leading order term. That's the claim of the main term. So this gives explicit calculations, at least in a leading order term of this multiplicative structures. And this holds in the case where this L divided by K and L prime divided by K is small. So I want to prove this main lemma. And the proof is the following. So we take, so as I said that an element of the player model we can calculate by just taking its value as a rational point. So now I want to detect it at this point. This minus is in this. So what is this? So this is actually something like a triple M2 product of this in this step. So you have this point. This point is L vector divided by K, and this is Lx, and this is L0, and this is Lk. And then this exponent of T is actually an area of this triangle. That's the definition of the M2 product. And this calculation is really similar to this concept calculation. When we first proposed on Camilla, we found this theta functions. But we just use for the leading of the sum. So we calculate this triangle, and this Lk has a slope K. And then this triangle is just calculated by this formula. It is calculated. So now I want to take this this product and take its value of x. I'm sorry, and minus is always wrong. This just take a sum of this k half x minus L divided by k square plus k prime half x minus L prime divided by k prime square and higher order. And then we have these two quadratic expressions, and it is elementary calculation, high school calculation. You can complete the square, and it is this that k plus k prime divided by 2 and k plus k prime divided by k plus k prime square plus some constant. So this is a calculation of the product in a leading order term. So we have proved this. Now once we have this reference, the proof of finite generatedness is rather easy. So what we have to prove for the finite generatedness, we start from some element here, which has rather big denominator. And then we want to try to show that the element with big denominator is a product of element with smaller denominator. Right? So suppose that there's something like you have a k plus k prime is something like bigger than capital N. And you can take k and k prime, so that k and k prime both are smaller than capital N. And this guy is a given one. So this formula explicitly means that the element with big denominator is a product of one with smaller denominator modulo higher order term. Then for higher order term, we can repeat the argument. And we can use this addict convergence so that any element in a big denominator is contained in a product of element of smaller denominator. So that's the proof of this finite integral. And you see that these arguments I just explained so far does not tell so much about the fact that there is no signifier. It almost in a parallel way apply to the zero x defined relation, except we have to construct that.
Including the work of algebraic Floer. Yeah, right.
I mean, so we need to use the fact that we have x0 or x1.
So just take the Floer to the values is that because 4 left to the 4. So on the mirror side, that will not get any algebraic cycle. I mean, if all cycles are algebraic, then you get no Lagrangian. It's all algebraic. On the mirror side, everything will be Lagrangian. There won't be any.
I mean, I just want to use the fact that you have two Lagrangians, and 0 and 1.
Yeah, it means that you already assume that
Yes, yeah. Because these are complex graphics, where the mirror is another graphic.
so it's kind of generic form.
So it's not generic point. Generic point is the mirror is not a graphic. It's just a cable.
Yeah, okay, that's what I'm saying. Okay.
Yes.
So
Yeah.
this is a kind of fixed.
Yes. So in the case of Lagrangian variety, since actually we know that the homogeneous symmetry, and also even in my paper on 1998 or something, we found that linear Lagrangian, this gives the theta functions. So this proof does not so much new in that particular cases. But the point is that this kind of argument, you don't need to use this theta function. If you have this kind of W, and you have this integral function up there, or 2 to get some very competitive being, using just only your answer. And this very competitive being is supposed to be a mirror. So that's the point. Okay, so now we have this. So now this theorem 3. This proof of theorem 3 is a bit unsatisfactory for me because it's a bit kind of cheating. So how to do it? So we have to prove that this is an isomorphism. So now we take this FK. It's a somewhat called in a type, and it gives the line boundary over this projective, and then you prove up. It gives a line boundary on the T2M check. It's a SYG mirrors. And what I want to do is to compare the rank of the sections of the OK, and the rank and the rank of A. Rank K part of A. And this section you can calculate by Riemann law. And it is just a K plus. And in a simplest example, I just explained what I usually show that it is K plus power N. And the rank of Floer homology is actually the number of rational points. So it is the same thing. So it implies that the sections, this guy is equal to the rank of this A. So it implies that this map is nothing. But so if you want to generalize this proof to the case of general SYG calculations, the point one need to see carefully is the following point. So I just constructed this map in a kind of set theoretical. Each point in SYG mirror gives a point in this 45 line. And if one can prove that this map is actually a morphism of complex manifold, then you can do this kind of argument. you need to compare this, length of line bond, length of section of line bond with the length of this, they will keep up. And that calculation here, Riemann lock in this case is just you need to calculate sigma.
I mean, in the brand is the other characteristic. How do you know that I am someone?
And on this side, T2N check. T2N check. You can calculate out just T itself. So T1 is something like in this simple example, T1 is 1, and K is technically K. This is a kind of easy calculation. And the point is that this rank of A, degree K part of A, is calculated quite independently. It's just rank of player mode. And in this case, rank of player mode is easy to calculate because it's the number of induction form. It's a rational form, number of rational form. So that is the argument. And as I said that once we know that a similar mark is a morphism of complex manifold, I think one can do the same calculation because we can calculate the Riemann law. C1 can calculate and the number of rational forms can calculate. So one can go through this proof. But the point is that I don't know how to. So the proof that this kind of maps is a morphism of a variety is slightly non-trivial because we construct this homogeneous ideal, so it's just a set-vector map. And so I need to show that this set-vector map is a complex analytic map. And maybe the best way to prove it is using some very version of the family player Monty. You can move this. You can move this point and you can reduce how this player Monty looks like. But this very version of the family player Monty is actually easier than after version of the family player Monty because we need to do it only locally. So the main part of the family player Monty is to understand wall crossing, and we don't need wall crossing because we have a global structure already on this project for geometric version. So we have this set-vector map, and we need to see this set-vector map only locally to show that it's a complex analytic map of complex analytic variety. So it gives some help, but I don't know how to work out this kind of thing in a marginal case, and that's a difficult point. So now let me go to the last point. So that this M gives so you have this another Lagrangian. You take this MK, and if you have chain complex, and then this gives so first of all, if I want to prove that this is going to give some kind of ATK factors, that automatically from W. So if you consider this infinity structures among M's, then this construction automatically implies that this composition gives this composition of the quasi-coherent series. However, I cannot prove that this is isomorphic in this way. And the way I can do at this stage is using this result by Petrus and Sheridan. They gave some nice theorem about automatic generation. So what they prove is the following things. Suppose you have some x and something supposed to be a mirror. And suppose you take the kind of subcategory of this Lagrangians and another subcategory, and suppose they are isometric. And this subcategory somehow satisfies some nice condition, which is in a sense a bit enough big to look up all this weight of gravity. Then not only this, but also they prove that under this condition, this category is split generally. This category is A side. This is a paper by Petrus and Sheridan. And in this case, we can just take this F as a category of this generated by the scale of M. Then we can know that tautology that the mirror is this of this ample line boundaries. And this ample line boundary is big enough to have a required property. And then it split generates. And then in the S side, it also split generates. But I don't like this proof so much because it's a bit kind of easy for me. And probably if I decide to use that, there might be simpler proofs. So it would be better to have a better proof, but I don't know how to do it at this stage. And one of the difficult points is that this coherence issue. So I'm pretty sure that this is logic like this itself is a kind of equivalent of categories in a great generality. But so far, the only way to prove it is to use this result by Peterson and Shaders. So that's an argument. So maybe I have some more time. I just want to get one more remark. So there's another possible way to look up ring structure. We consider this HF, L0, LK1. And then there's HF, LK1,